Hello, good people. This is video number one for the comparison tests. As we go through the list, I just kind of want to let you know that I try to, and I guess College Board as well tries to put the tests in kind of the order that maybe you should apply them, you should check them, so that the easiest ones come at the beginning, and now we get into not necessarily more difficult ones, but certainly more involved in the application of these tests for convergence. So we're going to start with the comparison test. And actually, this one I like to call the direct comparison test. So this is the direct comparison test. And we're directly going to compare one infinite series to another infinite series. So we have two infinite series. And let's say one of them, which is a sub n, has terms a1 plus a2 plus a3 plus yada yada forever, right? And the other one, b sub n, has terms b sub 1 plus b sub 2 plus b sub 3 plus so on and so forth. So I'm adding the terms, right? But the condition that we start with is that the terms in the series of b sub n are always bigger than or equal to the terms of a sub n. So if I were to plot them, and I'm not saying you have to, but if you did, and remember we're starting with 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So a sub, let's say b sub 1 is here, and this is b sub 1, and then here's b sub 2, and here's b sub 3, and b sub 4, b sub 5, b sub 6, and when I kind of see that they're leveling off, and so what we're assuming at the beginning is that a sub n is less than or equal to b sub n. So if I were to plot the terms of a sub n, they would be less for every, or less than or equal to, right? So maybe I could have something like this, but for the most part, b sub n bounds the terms of a sub n, of the a sub n terms, right? So b sub n is quote unquote bigger than a sub n. So if we start with that condition, then two things will happen. So if you look at the picture, think about it. If b sub n converges, if the whole series, if I add all of these numbers and they add up to a number, then a sub n has to converge as well because a sub n has smaller terms. So if the bigger terms add up to a specific finite value, then the smaller terms have to add up to a specific finite value. And so we can say that the series a sub n also converges. Conversely, if I know a sub n, the lower one, the smaller one, the blue one here, diverges, well, then the red one, which has bigger terms, when I add it together, also has to diverge. And so we're going to call this a convergence divergence test by directly comparing one to the other, right? So it all has to do with which one am I starting with, what do I know about one, and can I reach a conclusion about the other. So we're going to look at numbers 1 and 2 and apply the direct comparison test. Then we'll take a break, we'll come back, and we'll do some more examples. So how do I know I'm given one equation, right? How do I know what the other infinite series is going to be? And so usually we pick an infinite series that quote unquote looks like it, but is more easily solvable, right? So I would look at this and I would say, hey, if this was the series, this would be easy to evaluate the convergence and divergence of this series because I know that this is a geometric where r is 1/2, that's less than 1. So I know that it's going to converge. Now, out of these two, which is the bigger one? Which is the b sub n? Well, if you think about fractions, the bigger the denominator, the smaller the fraction. So that means this is my b sub n, and this is my a sub n, because 1 over 2 to the n is a bigger value than 1 over 3 plus 2 to the n, right? If you think of fractions, if I have 1/4 versus 1/10, 1/4 is bigger than 1/10. However, the denominator is smaller than this denominator. Well, here, this denominator, which is 2 to the n, is smaller than 2 to the n plus 3. However, this is a bigger fraction value than this. Oh, so I know that the bigger one converges. I know that b sub n is greater than a sub n. So therefore, if the bigger one converges, then the smaller one has to converge as well. So I can say this series converges by direct comparison test. I'm, I'm directly comparing it to another series whose outcome I know, and I'm choosing a series that I can directly compare the other one to. I notice that this purple series has bigger terms than the original series, and it converges. So therefore, the one with the smaller terms has to converge as well. That's the direct comparison test. Okay. When I look at this, again, I'm trying to figure out what would be a good comparison infinite series. And I would think that something like this would work. Again, I have another geometric series. R is 1/4. That's less than 1, so therefore it converges. But I have a problem because when I compare these two terms, this time this is b sub n and this is a sub n. This one's bigger than that one. So if the smaller one converges, that really doesn't tell me anything about the bigger one, because the bigger one could converge or it could diverge because it's bigger, right? So selecting this infinite series as the partner to this one, it really didn't help me out. Okay, so that was nice, but that didn't work. So what if we chose this series? Remember, you can choose whatever series as long as the one you choose, A, you know the outcome, whether it converges or diverges, and B, you can directly compare it to the one you have. So I'm going to choose 3 to the n. Why would I choose 3 to the n? Because this is a geometric with r equals 1/3, which is less than 1, and therefore it converges. But when I compare it to this one, well, now the original function is the one that is smaller. I'm sorry, is the one that is bigger. I'm sorry, is the one that is smaller than my partner series. So now this is my b sub n, the bigger one, and this is my a sub n. How do I know that? Again, when I look at the denominators, when I take 4 to the nth power minus 3, I'm going to get a bigger value than if I take 3 to the nth power. So therefore, this whole fraction is bigger than that one, so I can do this business. So b sub n is bigger than a sub n, and if this one converges, if the bigger one converges, then the smaller one has to converge, and I can say that that converges without hesitation. Converges because of direct comparison test. So what do we need to do with direct comparison test? We need to find I used to call it a buddy. What's the buddy series for this? I need to find a series whose outcome I know and that I can directly compare with the original one. And as long as I know what happens with the one I chose, and as long as I have this idea for convergence and the opposite idea for, or the converse of that for divergence, I can figure out the convergence or divergence of the original function by just directly comparing them. That's what the direct comparison test does for us.